So we'll start with the first one. I've got it here. And the red graph is your basic square root graph, the one that you know already. And they've got a point labeled. We're going to label it on here. Square root of 16 is 4, so you have the point 16 comma 4. And one of the things that we're going to start doing in this unit is showing some of our work of how points are changed. So if I had, on the blue graph, for example, if on my red graph I had 16 comma 4 to begin with, it's going to get changed to something new. And if I look at my blue graph, I've got a 3 out in front of my square root. That 3 would multiply my y values by 3. So if I consider 16 comma 4, and I multiply my y values by 3, I would get 16 comma 12. And you notice that's the point they have labeled as well. What about our green graph? What happens to 16 comma 4 on our green graph? Well, now we have a 2 in front, so we'll show our work above the arrow saying what's going to happen. Our y value is going to get multiplied by 2, and we get 16 comma 8. Sure enough, that's the point they have labeled as well. Orange graph, 16 comma 4. What happens to it? We're going to multiply our y values by half, 16 comma 2. And finally, on the purple one, that 1/4 means we're going to multiply our y values by 1/4. Giving us 16 comma 1. Now this is exactly the same as what we saw in the parabola to begin with. So it should be fairly straightforward in that sense. It's outside the function. It affects the y value. And everything outside of the function happens to be exactly as you see it, right? If you had a +4 at the end, we moved it up 4. Now if you have a 2 out in front, you're going to multiply your y values by 2. And this idea with the arrows is how we're going to start showing some of our work. Because you would know what points are on your original graph. Now, just one point wouldn't be enough to graph all of these. You probably can see you would choose 0, 0 as well. Okay? But what happens when you multiply anything by 0, 0? It stays. So with this point and that one, we would be able to draw the graph. We'd be able to draw each of those graphs with 2 points, and you already know the basic shape of what a square root graph looks like. These ones just have been stretched or compressed. And so with this type of transformation we call a vertical stretch or compression. And the way that it's described, if you visualize it, everything's sort of attached to the x-axis. If you stretch, you pull it away from the x-axis. If you compress it, you squish it towards the x-axis. If you have part of your graph on either side of the x-axis, it gets squished from both sides together or pulled away from both sides together. But now we're going to look at what happens when there's a number inside the function. Okay? The point that they've labeled to start on the red graph is 4 comma 2. Now, when we did translations inside, you saw a +2 inside your function. Normally, you would have been like, oh, I want to go 2 to the right. But it was the opposite. Now, with the blue graph, we see a 4 inside the function. Your gut would probably say, oh, if we multiplied y values, we should multiply x values by 4 here. But that's not going to be the case. In fact, if I start with, on the blue graph, 4 comma 2, something's going to happen, and the point that they've labeled is 1 comma 2. So we obviously haven't multiplied by 4. Some of you probably say, oh, we divided by 4. Yes. But we're not going to use dividing. Instead, we're going to say we're going to multiply by, what do I have to multiply by to be the same as dividing by 4? 1/4. And that 1/4, the reason we're going to go with the multiplying is because it's multiplying by the reciprocal, which will work out nicely when we have fractions. So on the green one, take our original point 4 comma 2 on our red graph. We've got a 2 inside. You multiply by the reciprocal. Label our blue point as well. Get 1 comma 2 on the blue graph and 2 comma 2 on the green graph. Then the reciprocal is nice because once you get to the orange graph, you have a half inside. What's the reciprocal of a half? I'm going to multiply x by 2. And finally, our purple one. We've got a 1/4, so the reciprocal is 4. And you get 16 comma 2. So with horizontal stretches and compressions, it's being pulled away from the y-axis or compressed towards the y-axis. We have to multiply our x-coordinate by something because it's inside the function. However, with it being inside the function, it's not exactly what you see. You're multiplying by the reciprocal. In particular, writing these instructions out is going to be nice when we start to do more things. Okay? Eventually, we combine everything. You're going to take a square root graph. You're going to flip it once, flip it again, move it to the left, move it to the right, stretch it this way, stretch it that way. What's the final graph look like? And so when we put them all together, working with these points like this will be a nice way to keep things organized and keep it simple. So here's an example when you have more than one thing. Again, they gave us 4 comma 2 as a starting point on our regular graph. So in showing our work here on the blue one, I would say, okay, I have 4 comma 2. What's happening to it? I look at the equation. I have a 4 on the outside. Outside of the function means that it's going to affect y. So I write above here, I'm going to multiply my y values by 4. Then I look, I also have a 2 inside the function. What is that going to do? That's going to multiply my x values by a half. Where does that point go then? 4 comma 2 changes to 2 comma 8. And sure enough, that's the point that they have labeled on the graph. On the green graph, we started with 4 comma 2. We see a 2 on the outside of the function. We're going to multiply y by 2. We see a 2 on the inside of the function. We're going to multiply x by a half. We end with 2 comma 4. And that's the point that's labeled. Two more to go. So on our orange graph, we have a 2.5. That means y is getting multiplied by 2, and the x is getting multiplied by the reciprocal, which is 2 over 1. That gives me 8, 4. And finally, on our purple graph, our y values are getting multiplied by a half. Our x values are getting multiplied by the reciprocal 2. Eight, 1. Good. And so we're going to combine this introductory video with example 1. Here's the graph of f of x. So they give us this graph in function notation. And we want to sketch the graph of y equals -1/4 f of x. So when looking at this equation, the first thing I notice is that that -1/4 is outside of the function. So I might write a note here that I'm going to multiply my y values by -1/4. If I had to describe this, this would be a vertical reflection and a vertical compression. Now, to find out what the graph looks like, we need to take key points from our original graph and then multiply the y values by -1/4 and see where those points go. So one of the things you have to be able to do is look at your original graph and say, does it have any really, really important points that I just can't ignore whatsoever? Things where the graph changes or it's like characteristic of the graph. On this one, for sure, 0, 0. That's like where the graph changes direction. So one of the points I'm going to look at is 0, 0. There's lots of other points that I could choose on my red graph. However, some points are nicer than others. And I want you to think about what would make a point nicer compared to not nice. For example, I like choosing 4, 4. I don't like choosing 3, 3. They both seem nice. Do I have something against 3s? No, I actually quite like the number 3. I thought, grade 6, I thought it was like my luckiest number. It was like probably favorite number for 18 months. So it's like, really, I like 3s. But no, I wouldn't choose 3, 3, 4, 4. -8, 8, I don't mind that one, but I wouldn't choose -7, 7. Why? Why did I like those numbers over the other ones? Easier to divide by 4, right? Because if I draw the arrow, what's going to happen, right? We're going to draw how are these points changed, and above this arrow, I'm going to write out what I need to do. I need to multiply my y values by -1/4. Can you see that those ones are easier to divide by 4 than choosing 3, 3? Now, it's not wrong to choose 3, 3. If you like to label -3/4 on your graph, perfect. But if you want whole numbers, these ones would be nicer. Now, when I multiply my y values, well, this one stays 0, 0. This one's now 4, -1. And this one's -8, -2. Okay? And now we just have to graph this. Okay, I'm going to make a mistake, and I want you to say to yourself, would you have made the same mistake? Okay, you ready? So I'm going to graph 0, 0, and 4, -1. Would you have made that same mistake? Or, yeah? You see the mistake I did? I just went down 1 unit, and I went down 1 unit because I'm supposed to go down 1 unit. But what's the scale on my y-axis? Do you see that it's going by 2s? You're like, oh. So going down 1 unit, no, I have to erase it completely. Going down 1 unit would be here. -8, -2 would be there. There's our graph. Can you see that that graph has had a vertical reflection? It's been flipped over the x-axis. Can you see that it's had a vertical compression? It has been squished towards the x-axis. So flipped and squished. Squished. Yeah, and there's not one word for that. Okay? The question says, also state the domain and range of each function. I'm going to do this in set notation. The domain are your x values. It goes to the left and right forever. The domain is everything. The range, it has the smallest value of 0 and goes up forever. So we'd write y is greater than or equal to 0. For my blue graph, the domain is everything, and the range now has a maximum value at 0. So y would be less than or equal to 0. Now, everything in this question was done in function notation. And what I mean by that is they said, here's the graph of f of x in function notation. It could have been any graph. And then they wanted to sketch the graph of -1/4 f of x. So I'm going to add to this question a second part, state the explicit equation for each graph. And I'm going to underline this explicit equation part. This means no function notation in terms of x only. Did anybody recognize the red graph from our activity right at the beginning? Which one is it? Agreed? So that would be the explicit equation. It has only x. It doesn't have any function notation. So if the function was y equals absolute value of x, does it make sense that the blue equation is just the absolute value of x with a -1/4 in front? Because the question said do -1/4 f of x, we're just replacing the f of x with the actual equation. Okay. Question for practice is number 3.